Hello and welcome to video number 2 of building a Class E transmitter. The first video we talked about the scope of the project, which is building an 8 MOSFET Class E transmitter for the amateur radio 75 meter AM band. And Class E is high fidelity, high power, high efficiency, and cheap. So you really can't beat that combination. So in the first video we talked about this duty cycle adjustment board, and I finished it today. And the inputs to this board are power, 12 volts in here. The VFO signal source comes in here, just a sine wave. And the output comes off of these two SMA connectors for the roughly 40% duty cycle square waves that are 180 degrees out of phase. Very important for this project. So, quick overview again. The first chip is a JK flip-flop. What that does is it takes a signal source from the VFO at twice the operating frequency and divides it in two onto two 50% duty cycle square waves that are 180 degrees out of phase. Those are then adjusted, the duty cycle is adjusted down by these two potentiometers using these two chips right here, and the output goes to the SMA connectors via these two low impedance MOSFET drivers, IX DD614s, one on each side, one for each phase. So there we go. Let's take it over to the bench, and I'll show you the square wave. I'll show you the waveforms that you'll want to see when you build your own project. So let's bring it over here. So we're using an oscilloscope, DDS VFO. And if you look down here, it's set for 7740 kilohertz, which is twice our operating frequency of 3.87 megahertz, the AM calling frequency on the West Coast for 75 meters. Hook up a few wires here. Put the scope leads on. Actually, we'll start out with the signal source. I'll show you the signal coming into this board. So I'll hook it up right here. Apply power. And here we go. We have a simple square wave, a simple sine wave. And if you look at the frequency when it comes in, get my triggering set here. Work with me here. Okay, 7.74 megahertz. 7.74, which aligns up with the DDS VFO. So coming in is that sine wave, and coming out, let's hook the probes up to the SMA connectors. If I can get them in there. There's one. Right down and now. All right. Let's adjust this down so you can see both waveforms. Triggering up here. Okay, now if you look at those two square waves, they're coming in at 3.87 megahertz, which is exactly half of what we're putting into it. The waves are 180 degrees out of phase, so when this goes up, this goes down. That's what that means. And the duty cycle is less than 50%. So if you look at this, the difference distance from here to here versus the upside from here to here, this is about 60%, this is about 40%. And that's what you're looking for the highest efficiency on these transmitters. Now, you adjust that duty cycle by, like I told you before, by adjusting those two potentiometers. And I'm not going to adjust those right now to show you how those waveforms do change, and they do change, because it was a dance trying to get these adjusted that way. When I built this board, I didn't build it using a custom, printed circuit board. I used it on just a regular circuit board with wires running everywhere and everywhere. I did my best to avoid parallel wire paths, but for some time, sometimes it's just unavoidable. And the problem with that is you have induced currents and interference on both phases. So when the duty cycles are mismatched enough, there tends to be some interference and this thing gets a little squirrely. But anyway, I got it to where it should be. Now, this is going to be really key at the end of this project. When this transmitter is all built, what you want to do, there are two, like I said, two phases here, and there are two drain buses that supply all the RF energy to the antenna. You want to make those drain currents matched as closely as possible. If they're close enough, I'm going to leave it alone. But if they're too far separated, I'm going to have to adjust this to get the currents to match a little bit. So we'll see at the end. If need be, what I'll do is I can redo some of this board and just to make it so that interference isn't there. We'll see at the end of the project how this all goes. But the good thing about this box is that I made it detachable from the transmitter itself, so it won't be that big of a deal if I have to make any changes. So in the next video, what I'm going to do is build a crystal oscillator and buffer that will replace this DDS VFO and will drive this duty cycle adjustment schematic rather than using that. It's just a personal preference. It's not required, but I would much prefer just to have my own stuff in there. And this is 7740 kilohertz, same frequency as this right here. Same function, just homemade. Again, another board that'll just plug into this one. So that's it. We'll see you in the next video and go from there. Thank you very much.